Good morning, everyone, and welcome to the 34th International Materials Research Congress here in 2026. Today, we've got an explainer that dives into some really fascinating first principles insights. We're going to unpack the structural, optical, and electronic behavior of titanium manganate, or TiMnO3 perovskite.
Just to give credit where it's due, this comprehensive research is the result of a fantastic collaboration. We're looking at dedicated work from researchers at the Educational and Cultural Institute of Hidalgo alongside the Autonomous University of the State of Hidalgo.
Okay, here's our roadmap for today. We'll start with the introduction and our main objectives, move into the computational methodology, and then walk through our structural results, electronic properties, and optical properties before wrapping it all up with our conclusions.
Let's jump right into Section 1, Introduction and Objective. Our primary goal here was to deeply investigate TiMnO3 using precise first principles calculations. And why does this matter? Well, understanding the fundamental atomic properties is absolutely critical, because perovskites with these exact characteristics hold immense potential for next-generation electronic and optoelectronic devices. It's a really exciting space.
But to uncover those properties, we needed a highly reliable framework, which brings us to Section 2, Computational Methodology.
We built our foundation entirely on density functional theory, or DFT. Using the Siesta computational code, we optimized our parameters with a generalized gradient approximation, specifically the PBE functional. And to guarantee everything was completely reliable, we ran rigorous convergence tests and applied the Monk-Hurst-Pack scheme for high-symmetry K-point sampling.
As you'll see, our computational pipeline followed a really strict logical sequence. We started by setting up test wave functions, moved through a full structural optimization, and finally executed the complex calculations for our band structures, density of states, and the dielectric function. With that rigorous methodology locked in, let's look at what we actually found, starting with Section 3, Structural Results. The crucial anchor for this entire study is the optimized equilibrium lattice parameter, which we pinned down to exactly 3.945 angstroms. To put that into perspective, this specific value is huge because it represents the most energetically stable, absolute minimum energy configuration of the TiMnO3 system. Achieving this structural equilibrium was our necessary first step. Think of this precise geometric architecture as the absolute foundation. It literally dictates the behavior for all of our subsequent electronic and optical calculations. Building directly on that very stable physical structure, we transition over to Section 4, Electronic Properties. Now, the absolute standout discovery in this phase is the presence of a zero band gap. In this specific electronic state, the valence and conduction bands actually overlap exactly at the Fermi level. So what does this mean? It means the material doesn't act like your conventional semiconductor. Instead, it shows distinct, highly conductive metallic behavior. By analyzing the electronic band structure and the corresponding density of states, we can undeniably confirm this metallic characteristic. That critical overlap right at the Fermi energy level provides the exact electronic states needed to position TiMnO3 as a highly promising conductive material. Okay, so next we needed to figure out how this material interacts with electromagnetic radiation. Let's look at Section 5, Optical Properties. To accurately measure this optical response, we zeroed in on the imaginary part of the dielectric function. This metric is a real game-changer for us because it gives a direct window into the electronic transitions, showing us exactly how the material absorbs light across different energy spectrums. And our data reveals multiple distinct peaks. This tells us there are significant electronic transitions happening right within the ultraviolet and visible light regions. Plus, the analysis highlights contributions that are tied to vibrational modes, extending deep into the infrared range as well. All of this comprehensive analysis naturally leads us right to our final summary. Section 6, Conclusions. Let's synthesize our primary findings. First, we achieved structural stability with that optimized parameter of 3.945 angstroms. Second, our electronic analysis proved a distinct metallic character driven by a zero band gap. And third, we identified broad optical absorption across the ultraviolet, visible, and infrared regions. Taken all together, these properties confirm the immense viability of TiMnO3 perovskite for future complex electronic and optoelectronic systems. If TiMnO3 can bridge the gap between structural stability and true metallic behavior, what other conductive secrets are waiting to be unlocked in advanced perovskite materials?
Thank you for your attention.